All right, so I'm going to give a talk about this framework that we've been building, myself and a number of collaborators spanning Berkeley, the Skylab, Stanford, NVIDIA, and many other companies. It's a framework we've been building to kind of make this concept of horizontal inference time scaling easier, or building multi-agentic systems maybe as a kind of more buzzwordy way to put it. And I guess the key point is we found, starting early last year, that if you kind of ensemble these LLM calls and you build networks out of these network calls, then you can actually push the quality and reliability frontier quite a bit. And I think we're starting to see these ideas manifest in systems like Grok 4, Heavy, Google with parallel thinking and Google DeepThink, 2.5 Pro Gemini. And so I think you're starting to see these things make their way to the fore, but we're still very, very early. There's a quality and reliability frontier expansion element, but there's also a price performance kind of cost reduction element. So can you ensemble calls to cheaper models and actually outperform larger models? Turns out you can, and to a very dramatic degree. So this framework with collaborators from IBM Research, Microsoft, as I mentioned, Berkeley, sponsored largely by help from Skylab, Berkeley Skylab. So first, I'll actually just motivate why this inference time scaling architecture research, like why is this even an interesting domain? What are some of the intuitions that motivate this? And yeah, as Tron mentioned, the cost of tokens has been deflating pretty dramatically. The cost to achieve the same level of intelligence, the same score on some of these benchmarks, has been going down 10x every year for the past 3 years. It's gone down 1,000x. It's quite dramatic. This is a trend, a pretty rare trend. At the same time, the model ecosystem has expanded pretty dramatically. A couple of years ago, there were only a couple of models. OpenAI's GPT 3.5 and GPT 4, for example. And any routing research was just among these two options. Now there's a very heterogeneous and diverse and variegated set of model options across many, many providers. And many times these generations of models, like the Claude 4 generation, actually come out with multiple models at once, kind of a small, cheap, fast variant, and then a heavy, smarter variant, right? And so there's this kind of notion of a Pareto frontier that's being defined. And in fact, actually, Gemini very explicitly invokes the notion of a Pareto frontier whenever they release their Pro all the way down to Flash or Flash Lite kind of family of models. And so there is this ecosystem, there is this landscape, and there's some notion of a frontier in this landscape. And these facts have motivated a lot of work on trying to understand the landscape. To that point I made about cutting costs, the difference in prices across these different models is actually quite dramatic. O1 Pro, for example, was $150 per million input tokens versus 3 cents depending on cache hit on DeepSeek R1. So that's a 5,000x, more than 5,000x difference. That's extremely dramatic. And so you can make 5 R1 calls, compose them in some way, and actually that would be cheaper than a single O1 Pro call. That's obviously changing. These models like O3 and such sometimes are actually cheaper than O1 Pro, but you get the idea. And so this has motivated a lot of work on routing systems like Frugal GPT, on kind of creating ensembles of network calls and aggregating in various ways. So like voting-based aggregation, best of n graphs, verifier prover structures, and some of those kind of classical ideas that came up in neural network research around skip connections, or around GAN-type structures with some almost prover verifier, discriminator generator. These ideas are actually coming back in interesting ways at this network call composition level. And yeah, so I won't go too much into this today. I'll just note these kind of facts, and also facts around specification and kind of the reliability, motivated some work on this framework called Ember. And I'll make one point about this, actually, since we have a few minutes. I think right now, arguably, the GPT-4 moment was kind of like the Wright brothers' Kitty Hawk moment. It was very, very exciting. I think it galvanized the entire field, but it's still the very early days. It took about 10 years to go from Kitty Hawk to the dawn of commercial aviation with Yanis. It took quite a while, and there were a lot of inventions and innovations were necessary to get from early demonstration of the technology to a very reliable infrastructure that could fly hundreds of millions of people per year. And so that motivated this work on Ember, largely motivated by, for example, Jan Stoica's work on specifications and others. And the idea was to build a framework that kind of achieves for this network of networks composition research endeavor what Torch helped contribute for neural network composition endeavors in the 2010s. Torch made it very, very easy to compose, and kind of express new ideas, and also made those new ideas run fast with parallel dispatch and some nice ideas undergirding it that were abstracted from the researcher. And so Ember is similarly trying to be fast to run, fast to write. This is actually a kind of banner from the Spark days. And Ember is actually named in that same family: Spark, Ray, Ember. It's a funny naming scheme. And just to give you a little bit of an intuition, these are the types of things that people do. There's kind of 3 different ways that people express these Ember graphs. This is the very simplest. It's kind of a Unix X expression, very, very short. It's basically, you can have an ensemble with 101 members, some certain model like GPT-4o, and then some temperature. And then you define that in a single line, and then you can reuse that system. And underneath, those calls are dispatched across providers in parallel, and the answer is returned quite a bit faster than if it was run as just a for loop. People have also defined these kind of hierarchical graphs where you can have a graph with multiple different sub kind of trees that themselves are spread across multiple providers. And here's kind of an even more intuitive class-based way of showing it, where you can have an ensemble class that is JITted, so it can, so an IR can be composed that can be run client-side or server-side. So you can optimize the execution of this graph over API calls, or if you're running things like VLM or SGLang locally, intelligently. And you can define ensembles, and those ensembles can go to judges, and the code can be written eagerly, but then run intelligently and kind of scheduled and parallelized. So I'll skip forward, and I'll just note, as we go into the next section, this framework was called an Inference-Time scaling architecture framework, not an agents framework. And I'll actually controversially note, I actually think that the classical definition of agents needs to be brought back. I think that we're often conflating desiderata that we associate with useful agents with the definition of agents. I think memory and tool use are properties of a useful agent. They're not inherently properties of an agent. In the classical RL definition, an agent is defined in terms of this framework with an agent, an environment, and some concept of actions that the agent can make on the environment and rewards that the agent can receive. Via this lens, the work that even Adept AI was doing a few years ago with large action models, which were really just a single model, that was taking in observations and producing actions, that was an agent in a limited way, all the way up to these kind of compound systems with many, many calls or multi-agent systems. That notion of it being a compound system is orthogonal to the concept of an agent. I like this definition quite a bit, and I think the properties of useful agents like memory, the ability to use a myriad of tools, et cetera, I think those are desiderata that we want from a great agent. Those aren't necessarily part of the definition of an agent. So that's my point there. OK, great. So with that, I think we're out of time for the lightning talks. So now we're going to proceed to a panel with myself, Ramin, Tren, Bill, and also Igor from Grok.